I'm going to teach you about the points of concurrency on this video, and I'm going to warn you it's going to be a little bit long because we have 4 different types of points of concurrency. I'm going to try and get it all in one video. For this video, you're going to want a ruler of some kind. If you have one that's clear, that is going to be a little bit easier. If you don't have a ruler, it's not the biggest deal in the world. I'll show you, or you can just kind of estimate what we're doing. But if you don't have a ruler, you might want to grab at least maybe an index card to use as a straight edge. So, all right, so first up, let's back this out a little bit. All right, so first, to make sure that you even know what a point of concurrency is, if I was with you, I would ask you if you know what it means to concur. And basically that is when something agrees. So you meet up on a common decision would be a good way to think of that. So when we talk about a point of concurrency, that's going to be a point that is an intersection. So we're going to have lines, rays, or segments. We're going to just deal with segments today, but it could be a line or ray. But it's where we have 2 or more segments that meet at the same point. That's called a point of concurrency. So we're going to be doing 4 of them. We're going to use perpendicular bisectors, angle bisectors, medians, and altitudes. So what we're doing is we're looking for where those segments meet, which is where they concur. Okay, and then each of those has a special name to it. All right. If you didn't print this out, then I would recommend pausing the video and getting the information written down, as well as drawing a triangle, because we're actually going to do find the point of concurrency for these different triangles. So if you need to pause the video, then please do. Okay, so first thing, we're going to find the perpendicular bisectors of this triangle, and then where they meet is called the circumcenter. All right, so first up, we need to find the perpendicular bisectors. All right, so perpendicular means that it's going to meet at a right angle. Bisector means it's going to cut it in half. Okay, so triangle has 3 sides, so there are 3 perpendicular bisectors. So we're just going to do one side at a time. So we'll just start with this one, since this is the way our paper goes. So what I want to do first is find the middle of this piece right here. Now, if you have a ruler, you could just measure it and then figure out the middle. If you don't have a ruler, you could always just fold your paper over, which is a very valid way to find the middle. All right? So since I just did that, I might stick with this. Okay, so I just folded, and looking through, you can see the shadow here. So I just had these 2 points meet with each other. They're lined up. I'm going to crease it just a little bit. So this right here is the midpoint of AB. All right, so now what I want to do is draw a perpendicular line that cuts this one in half. Well, I already know where the halfway mark is. So now what I need to do is draw a perpendicular line. So perpendicular means it's going to meet at a right angle. An easy way to do that, if you have like a straight edge, is you could use the corner. And if you line up this one and this one, then that's where would make 90 degrees. The other thing you could do is use the marks on your ruler. Like I'm going to use this, let's see if I can get out of the light a little bit. So where this 2-inch mark is, if I line that up with my line, then I know this is going to be perpendicular. If it was like this, it's not lined up with the bottom of the triangle, so I know that that's not going to be at the right spot or at the right angle. So I'm going to go with this, and I'm going to make a segment. And you can see that I made it longer than maybe I needed to, but we'll see why in a few minutes. So what I know is that I cut this piece in half, so this side is congruent to this side, and I made a right angle right there. All right, so now what we need to do is do the same thing for this side and this side. So it might be easier to turn your paper. So I'm going to do side AC now. So I first need to figure out the middle of AC. So again, I'm just going to line this up if I can. I think that's a pretty good job. All right, so this, I just marked the middle, which is right there. And now, so I know that this side is congruent to this side because I just bisected that. And now I'm going to get a straight edge, and I'm going to draw myself a line that is perpendicular. So I'm going to draw it right there. Now, if we look at what we have so far, remember that what we're trying to do is figure out where the three perpendicular bisectors meet. So that's why you sometimes need to go longer than what you think, because it could be outside of the triangle. All right, so now we need to do the same thing for side BC. So I'm going to try and find the middle of BC, which I think is right about there. So I'm going to mark that. So now I know that this side right here is the same length as that side right there. And now I'm going to draw a perpendicular line. So I'm just going to line up my ruler, and again, we're trying to get these things to meet. So you want to make sure that you extend it far enough. All right, I did pretty good, off a smidge, but that's all right. All right, so here's the deal that happens here. All right, these pieces here are, oh, you know what? I forgot to mark that this was a right angle on that one and also this one. So I made a perpendicular bisector for each side of the triangle, extended it, and they all met right out here at this point. So these are all perpendicular bisectors. So I'm going to label one of them. So this is a perpendicular bisector. And they all met at the point right there, and that point is called the circumcenter. So that is the circumcenter. So the circumcenter is the point where the perpendicular bisectors meet. Okay, so they intersect at a point. So here are the special parts of this. So they intersect at a point that's equidistant from the vertices of the triangle. I'll explain to that in just a second. It can be inside, on, or outside of the triangle. Depends on what kind of triangle it is. Well, since ours met outside the triangle, we know that this triangle is obtuse. But if we look at it, we can see that's an obtuse angle. So if we did a right triangle, it would actually land on the triangle. If we had used an acute triangle, it would have landed inside. So it's kind of neat how that happens. And then the last thing that I want to show you, which is what we're talking about. I don't know that you necessarily have a compass at home, but this is a compass, and you may know that it makes circles, is what it does. But if we put the point on the circumcenter, we can make a circle around, I'm not doing a good job here on my circle, but we can make a circle that goes around the shape. So when this says it intersects a point that's equidistant from the vertices, so here's the deal. So the distance from the circumcenter to point A, so this distance right here, is the same as the distance from the circumcenter to C, which is right there, which is the same distance from the circumcenter to point B, which is right here, So if you realize what's happened here, we were able to draw a circle around the triangle that hit the 3 vertices of the triangle, which means that each of these is a radius. So from the circumcenter to each point of the triangle would be the same distance. All right, so that is what happens when we use the perpendicular bisectors and they all meet at a point. All right, moving on to the next one. So now we're going to look at the angle bisectors. Okay, now this one's going to be a little bit harder to do. And again, if we were together, we would be using the right tools. So what's going to happen here is we're trying to bisect the angle. So we need to cut these angles in half. So I am going to, again, just use paper folding techniques. So if I want to cut this angle in half, that means I want these 2 sides to meet up. So I'm going to fold, and then this is not easy, so I'm warning you. But I'm trying to fold, if you can see through, hopefully. Can you see through? I hope. So I'm trying to figure out where it goes through the angle and line, and the sides line up. Now, it doesn't mean that, so let me open this back up. It doesn't mean that B and C are landing on each other, but what I'm doing is I'm trying to cut this angle in half. So I'm folding it so that the 2 sides meet each other. So you can see that B is out here, C is over here, but I am trying to get these 2 to meet each other. All right, that is the angle bisector. And since I folded my paper, I'm just going to use this fold like this to draw my angle bisector. So what I just did is I cut this angle into 2 equal angles. All right, so now what I need to do is the same thing on the 2 other angles. So I'm going to go for angle B next. And again, it's not easy. So I'm going to find angle B, kind of pinch that down, and then I want the 2 sides to line up with each other. And I think I have it right there. So let's see. I missed angle B a little bit, but that's all right. All right, and then I'm going to use the fold to draw that one. So what I just did, I can tell this isn't perfect down here because I missed the vertex. But now this angle right here is the same degree measurement as that one right there. And then the last one is angle C. So I'm going to try and pinch angle C perfectly right there. But I want the 2 sides to match up. So I think I'm off a little bit on this one, but we'll see. Maybe it's not as bad as it appears. That one actually was better than I thought it was going to be. All right, so I'm going to use the fold here to draw my segment. So now I know that this angle right here is the same measurement as that angle right there. So I have 3 angle bisectors because the red one bisected angle A, the blue one bisected B, and the green one bisected C. Now, they all met almost perfectly right here inside of the triangle. So this is the point of concurrency. All right, now to label this, we use the angle bisectors. So these pieces are angle bisectors. And then they met at that point. And this one, where the angle bisectors meet, is called the incenter. So the incenter is the point of concurrency for the angle bisectors. So where the angle bisectors meet is called the incenter. All right, so here's the special parts about this. First of all, it's always inside the triangle. So it doesn't matter whether you have an acute, an obtuse, or right triangle, the in-center is always inside. All right. Now, what happens is that this point, this in-center, is equidistant from the sides of the triangle. So I'm going to take my compass again. So what that means is from here to the side of the triangle is the same as there, which is the same as there, which would allow me, all right, I'm going to try and do this. Let's see if I can do this better than, oops, I'm not doing a good job at all, but this compass is what I had at home, so yeah. All right, let's try it this way. Okay, that was a little bit better. I am usually better at moving the paper than I am moving the compass. So, all right, so here's what we ended up with, was a circle inside of the triangle. So what happens is very similar to the circumcenter. From here to here is the same as the in-center to that side, which is the same as the in-center to this side, because each of those is a radius. So we have the in-center is always going to be inside, and it's going to be the same distance to each side. Okay, so you might be kind of wondering, like, why in the world would anyone use this math? And actually, this is used all the time with planning and developing. So let's say that you are looking for a location for a hospital, okay? So things that would be important to the location of the hospital would be making sure that people could get there easily. So maybe for this one, maybe you're trying to locate the location of the hospital so that people from 3 different towns could easily get there. For this one would be the same distance maybe if there's 3 different roads and you want to put the hospital where the people have the same distance, whether they're on like 75 or 85 or 285, something like that, where you could easily get there. So if you were looking for a cell tower, okay, a location of a cell tower, because the area that a cell tower can reach is going to be in a circle. So if you place the cell tower right here, you would be able to reach these towns and then the surrounding areas. If you put the cell tower right here and these are your towns, you're not reaching the towns. So just different ways that this can be used. All right, so let's move on. So now we are on to the next one. So page 2. All right, so now we're going to work with the altitudes. If you know what altitude is, if I asked you what altitude is, you would probably think of an airplane and you would say the height, and that's absolutely true. So what we want to think of for the altitude is the height of the triangle, okay? Now, if we were measuring the height of something, we would do a right angle measurement, basically. So when you go to get your height measured, you're not leaning to the side. They tell you stand straight up. So you want to make a right angle. So what we want to do is we want to figure out the height of this triangle. So that means from C to this side. But we are not measuring the height like that. We would measure the height like this. So let me see, turn that off. Maybe that's better. I don't know, maybe not. Okay. So I want to go from point C. It's almost like we're dropping a rock that has a string on it, okay? So I want this to make a right angle down here. So I'm lining up the line on my ruler, but it also has to go through C. So maybe like right about there. So I'm going to draw that one. All right, so it makes a right angle. This would be the height of the triangle. It has nothing to do with cutting the bottom in half. So it doesn't have to bisect anything. It just needs to make a right angle and go through the angle. All right, so now I'm going to turn, and we could do the height from B. So from angle B to side AC. So I want it to be a right angle, so I need to line it up here, but I also need to go through the angle at the same time. So I think I got that right there. So this makes a right angle. It doesn't cut anything in half. This angle's not split in half. This is not split in half. It's not bisecting anything. It is just telling me the height, which would be the distance from this side to this angle. All right, now I'm going to turn it again so I can do the height of A to side BC. So again, I want this to be a right angle down here, so I'm going to line up the ruler and then slide it so that it is going through angle A. So if I do this right there, so this makes a right angle. All right, so I got them all to meet. I'm a little off, but it's pretty good. So the three altitudes meet right there. So to label this, these lines that we drew here, or segments, are the altitudes. So that's an altitude. And then the altitudes meet at that point, and that point is called the orthocenter. Now, the deal with this one is similar to our first one, where we got the orthocenter on the inside. That's because we were dealing with an acute triangle. If we had a right triangle, it would be on the triangle, and if this had been an obtuse triangle, it would have met outside. That's the only important thing about the orthocenter. Now, the reason why it is important is because it is taking the heights of the triangle and finding where they meet. But otherwise, you can't draw a circle inside, you can't draw a circle around, which is why it's called in-center, because you can do a circle inside. The circumcenter, you can do a circle around the outside, if you think circumference. But the orthocenter, there's not really anything that exciting about that one. So, okay, moving on to work with the medians. Okay, so now the median is kind of a combination, because the median goes through the middle of the side, but it also goes through the angle. So if you look back at our perpendicular bisectors, cut this in half, but it didn't go through the angle, okay? So this green line right here, cut this side in half, but it didn't go through the angle. For the median, we're going to find the middle of this side and then connect the middle to the angle. All right, so first thing I want to do is figure out the middle of BC. And again, you can do that with a ruler, although I do find the folding to be pretty easy and probably more accurate. So first thing I need to do is get B and C to line up with each other and the sides lining up as well. So I think that's a little bit better. All right, so I'm just going to crease that. I don't want to crease the whole thing. I just want to crease right there. All right, so I just marked the middle of BC. So I know that this piece over here is congruent in size to that piece over there. Now I'm going to take the straight edge and connect the middle to the angle. So I'm going to take the middle that I just figured out and connect it to angle A. And I get that. All right, now, I didn't cut this angle in half. I cut the side in half. It's not perpendicular. It doesn't have to be. It just has to be the middle of the side and through the angle, because that's what the median is. All right, so now I'm going to connect angle B to the middle of AC. So again, I'm going to fold my paper to try and get AC, And again, I mean, hopefully you're having success with this, but AC, and I don't want to crease it. I just want to like make a little crease, I guess, right there to mark the middle. So now I have the middle of that side right there. So I know that this piece over here is the same length as that piece right there. So now I'm going to connect the middle of AC with angle B, and that is going to be the median. So I'm going to connect those two. All right, so far I've got those two to meet, which is not that big of a deal because two lines will meet if they cross each other, right? The big thing is making sure the third one works. All right, so now we need to find the middle of AB and connect it to side C. So the middle of AB, so I'm going to fold this over. Whoops, I'll go a little bit more. Okay, so I want AB to match up and just do a little crease right there. So now I have, this is my midpoint right there. So this point cuts this side and this side into equal pieces. So now I want to connect the midpoint to angle C. So I'm just going to grab the straight edge and I'm going to connect the midpoint with angle C. And I did that. Oh, I did pretty good on that one. All right, so the three medians met right here. So these guys concurred right there. So to label these, the segments that we drew, those are all medians. And then they met at this point, which is called the centroid. Now, this one is very cool. All right, now you're going to have to think about this and just absorb it and, you know, trust me on this a little bit. But I think if you took measurements, it would work as well. Okay, so first up, the centroid is always inside of the triangle. Okay, so just like with the in-center, it doesn't matter what size, what kind of triangle you have, it's always going to be on the inside. But here's what's cool about this one. Okay, the centroid is, if we take the distance right here, I'm looking at the green one, the distance right here, this centroid is 2/3 of the distance from the point to the side. Okay, so what that means is, let's see, I'm going to use the pencil on my, whatchamacallit here. All right, is if this side right here is 10, I know this piece down here is 5. So this whole piece is 15. So 2/3 of it is between the centroid and the vertex, and 1/3 of it is between the centroid and the side. So let's say that I told you this blue segment right here was 18 inches, whatever you want to call it. If this is 18 inches, then what I want to do is break it into thirds. So 18 divided by 3 is 6. So that tells me the short piece is 6 and the longer piece would be 12. So from the centroid to the point is 2/3, and from the centroid to the side is 1/3. Okay? Another thing that could happen is if I knew, let's say that this side right here was, we'll just say this side right here is 4. So if this piece right here is 4, I know this piece over here, because this is from the centroid to the side, is 4, then the centroid to the vertex would be 8, and the whole median would be 12. So that's just a neat thing that happens with the centroid. So what we say is that from the centroid to the vertex is 2/3, so this is 2/3 of the whole piece. And then from the centroid to the side is 1/3 of the whole piece. So if you take the length of the median and divide it by 3, the smaller part is going to be 1/3, so that would be the answer, and then the other part would be twice that. All right, so that takes care of the points of concurrency. So just to review, we had 4 different kinds, and each one was a different line segment, and it met at a different point, and those points are named. I don't know who decided, but someone decided that those would be the names for the points of concurrency.